In this lecture, we'll look at evolution and the process of natural selection. We've talked about the microscopic mechanism of evolution, which is the genetic information in DNA. That discovery was made in the 1950s by Crick and Watson. If you go to Cambridge, you can visit the Eagle Pub, as I did just last year, and that's where Watson and Crick first announced to surprise pub goers their discovery of the genetic code, the genetic information of life, about 50 years ago. The macroscopic theory of evolution, which is to say how entire organisms evolve in their environment, was put forward by Charles Darwin. Darwin lived through most of the 19th century, and his contribution is well summarized in the words of the great evolutionary biologist Ernst Mayr, who lived to the age of 100. Darwin developed a new set of principles that influence thinking of every person. The living world, through evolution, can be explained without recourse to supernaturalism, cosmic teleology. An intrinsic process leading life automatically to ever greater perfection is fallacious, with all seemingly teleological phenomena explicable by purely material processes. And determinism is thus repudiated, which places our fate squarely in our own evolved hands. Evolution is the concept that all life on Earth began with a common ancestor, and the gradual accumulation of inherited genetic changes to the genome is a consequence of natural selection, leading to the diversity we see in forms of life on the Earth today. We learn about evolution primarily through the fossil record, and we recognize that the fossil record does not exist for most of the history of life on Earth, when life was microbial or single-celled without even multicellular bacterial mats. So there are isolated fossils available to us from about 2 or 3 billion years ago. But the main fossil record only starts after the Cambrian explosion and gives us about a 500 million year of sampling. Also, we should recognize that the process by which a living creature after death is interred and its tissues turned into stone is a slow process that doesn't happen with any reliability. Less than 1% of all living creatures leave fossil remains, and most of those fossils are not complete. So the fossil record is patchy and fragmentary, and it's taken a long time, a century of research, to piece together this story of life on Earth. The modern science of evolutionary biology studies both the lines of DNA, so the genetic material at the level of individual atoms and molecules, and also the fossil evidence of whole organisms to reconstruct the evolutionary processes that have sculpted and produced modern species. For example, evolutionary biology has established that marine mammals evolved back into the ocean from terrestrial mammals. We can see convergence in evolution in some of the forms that marine mammals have: their ability to navigate in their environment, the shapes of their bodies for efficiency moving through the water, and their tails for propulsion. We can map out the evolution in terms of the fossil record in the oceans going back this 500 million years. The DNA record is important here too. Although DNA does not survive in most long-dead specimens, analyzing the genome of species is a way of mapping backwards to what their evolution path might have been. It's the genetic blueprint of an organism. Comparing DNA evidence allows evolutionary biologists to see how much of the genome is shared between species, and therefore pinpoint where the genetic code differs, and map back the tree of life. The fundamental process here, as outlined by Darwin, is natural selection. Natural selection acts by preserving genetic mutations that confer on that organism a competitive advantage for survival and allow it to persist, endure, prosper, and perhaps dominate. Natural selection is driven entirely by environmental factors. A beneficial mutation or change in the genetic material is any one that helps an organism either survive long enough to reproduce, ensure that its offspring are more likely to survive and reproduce, helps them hunt or scavenge or gain food or use energy more efficiently or effectively, or evade predators, such as camouflage. As we hear from Darwin's own words, natural selection can only act by taking advantage of slight successive variations. She can never take a leap, but must advance by the shortest and the slowest steps. This long series of slow, small steps can eventually lead to entirely new life forms, a process that's called speciation. We can take examples of this, and these are the examples that give most of the power to evolutionary biology, because we can see Darwinian natural selection in operation in the world we live in. For example, rabbits that live in a snowy environment will occasionally produce offspring with genetic mutations that make their fur a different color. So with this genetic variation producing difference in fur color, few of the dark-furred offspring will survive, reproduce, and pass on their dark fur genes because they stand out and are picked off by predators. Meanwhile, the light-furred offspring can evade predators and survive to reproduce and pass on their genes. So that beneficial gene is advanced. So in successive generations, the white rabbits will thrive, survive, and reproduce, and the dark rabbits will gradually be picked off and die out, leading to an overall change in the color of the rabbit population, completely sculpted by the environment. Another example, famous in biology, is the peppered moth. Survival and evolution of species are not only affected by the natural environment, but also by the human-caused changes to the environment, such as human industrial activity. In a famous study carried out over several decades, it was clear during the pre-industrial revolution that pale peppered moths in England outnumbered dark pepper moths. These populations of moths existed throughout pre- and post-industrial revolution England, particularly northern England, where most of the industrial activity was. During and after the Industrial Revolution, soot started to cover buildings and trees, and the dark peppered moths become more common because they can blend in more easily with the dark surroundings in the environment and the dark coloration on the objects in the environment. The poorly camouflaged form of the peppered moth is obvious to predators and so will not survive. However, a reversal in this evolution is then seen at the end of the Industrial Revolution into the modern age, where the populations turn again because cleanup efforts have gradually removed soot, coal is no longer being used as an energy source, and so the lighter colored moths have a selective advantage and survive. This wonderful little case study of evolution in action, in this case sculpted by human influence, is an indication of just how efficiently evolution is able to adapt to a changing environment. Regardless of the type of organism, natural selection is a fundamental mechanism at play in evolution, and it's driven by two major environmental pressures. One is the act of survival, having offspring and having sufficient offspring that they survive, and the other, related, is competition for resources. Fish, for example, lay thousands of eggs just so that it's likely that a relatively small number will survive. The kangaroo rat, for example, does not need to drink water and can exist on far less water than other mammals in other parts of the world, which is advantageous for survival in the desert. There are many examples of modern creatures, plants and animals, to show how they have adapted to diverse environments. They have to compete for resources, they have to pass on their genes. Environmental forces also sculpt the evolution of life on Earth in a cosmic global way. Because we live around a sun-like star, that sun-like star has an energy distribution that peaks in the visible range. The sun's radiation does arrive at the Earth in ultraviolet forms, where it's blocked by the Earth's atmosphere, and in infrared or long wavelength forms, where some of it gets through to heat the Earth's atmosphere. Vision, present in many animals, evolved to work at the peak region of wavelengths from the sun. So it's a perfect form of adaptation of the fundamental component of the way we navigate our environment that's perfectly tuned to the energy production of the sun. And photosynthesis, the fundamental energy mechanism used by many creatures on the Earth, evolved to use the radiation the Earth receives from the sun. Also remember that the abundance of oxygen forced life either to learn how to use this corrosive and toxic gas or perish. We imagine that evolution on exoplanets, assuming life exists on exoplanets, will be similarly sculpted by their cosmic environment and the nature of their parent star. We can imagine that stars which are dimmer and cooler than the Sun, like the many red dwarfs which actually correspond to the largest amount of habitable real estate for exoplanets, these are stars that emit very little radiation at visible wavelengths. Most of their radiation is in the infrared. So we can imagine that photosynthesis would function quite differently on a planet around a star like that. We can imagine that higher creatures like animals would actually evolve infrared sensors or infrared analogs to our eyes to be able to sense the dominant radiation from their star. Evolution is the concept that all life began with a common ancestor. Genetic diversity is spawned by mutation, by the spreading of the DNA, and by sexual reproduction. And then the progeny are sculpted or limited by the natural environment. This interplay between genetic diversity and the environment is the process of natural selection outlined by Darwin. There's a selective advantage conveyed on organisms which are better adapted to their environment, can use resources more efficiently, escape predation, and so on. Natural selection depends on the environment, and since the environment changes, natural selection is always culling the populations of creatures on the Earth in response to these changing conditions. This process continues to the day as humans alter their cosmic and global environment.